Okay, good evening everybody. So my name is Harri Niemi, so I'm giving now this presentation for second time now in English. As before, I'm going to talk about the quark-gluon plasma and the research that we are doing here at the University of Jyväskylä. We have actually two groups here. One is theory group. I also belong to this theory group. And then we have experimental group where this type of matter is studied experimentally, and our experimental group is actually part of ALICE collaboration, which is one of the large experiments at the LHC accelerator at CERN. So quark-gluon plasma is state of matter. So, and before we go to the quark-gluon plasma, I actually want to go a little bit through that what are the other states of the matter. So we can start from the solid state of the matter. So in normal conditions, constituents of the matter are atoms, and in solids they are bound together in this regular grid, so on the left-hand side of the screen. And these atoms are bound by electromagnetic forces. And now the question is what happens when we start to heat this kind of matter. So if we add heat or energy into this matter, so then actually these bonds get broken, and if we heat more and more, the solid melts and becomes liquid, and heat even more, it becomes gas. So the gas is the state of the matter where all these bonds between the atoms are broken. And now the question is that what happens if we heat even more? There are no more bonds between the atoms that can be broken, but if you look at the structure of the atom itself, it consists of atomic nucleus and the electrons that are surrounding the atom. And if we really heat enough this matter at sufficiently high temperatures, we can actually create a state of matter where all these electrons are detached from the nuclei, and the atoms, electrons and the nuclei, they form this kind of state of matter that is called plasma, where nuclei and the electrons can move freely with respect to each other. And this, for example, in the core of the sun, matter is in this kind of state. Temperature is something like 15 million degrees. But now the question is that what happens if we heat this even more? So electron is already a fundamental particle in the sense that we cannot split that anymore into other particles, but the same is not true for the nuclei. So the next slide. Nuclei is actually consists first of nucleons. These are protons and neutrons. They are not yet elementary particles, but these nucleons consist actually quarks and gluons, and these are new type of elementary particles. And now we actually are away from the realm of electromagnetic forces that was dictating the behavior of all the other phases or states of the matter what we are shown before. Here the force is actually strong force, and its theory is called quantum chromodynamics, or QCD for short. And now the question is that if we heat this matter even more to very extreme temperatures, can these bonds between the quarks and gluons, can they be broken? And the question is yes. So actually this theory of strong interaction says that if we start to heat this matter, so we, for example, add heat, and at these extreme temperatures, adding heat means that the energy can be converted to other particles. So eventually this nucleon matter, so on the left, it becomes very dense, and these nucleons start to actually overlap each other. And actually same result happens if we start to compress this matter. And the theory says that at sufficiently high density or temperature, actually this quark-gluon plasma forms, that these nuclei cease to exist, and the whole system becomes this kind of soup of quarks and gluons where they can move freely. They are not anymore bound in these nucleons. And this is really a new kind of matter, first in the sense that these constituents are now truly elementary particles, so they cannot be divided into other particles anymore. And second, that now the interaction here is really strong interaction. So interactions between quarks and gluons is dictated by this quantum chromodynamics. It's not anymore electromagnetic interaction. And now question is that can we actually study this type of matter in laboratory conditions? So Next slide. Actually, because this behavior is controlled by strong force, we need pretty extreme conditions that if we would be able to create significant amount of this matter. For example, if we take 1 cubic centimeter of QGP, this quark-gluon plasma, and we would like to make that by compressing normal matter. So the theory actually says that we would need 10 to 12 kilograms of matter. That would be 600 times 600 times 600 meter cube of iron, for example, and we would need to compress that into size of the sugar cube. And this is obviously this is not possible. Then how about heating? So still the theory says that we need temperatures that are order 10 to 12 kelvins. This is 100,000 times the temperature in the core of the sun, so this is pretty extreme as well. And the problem is that we don't have practical ways of making this kind of heating, but even if we wouldn't have energy, because the energy that would be required for such heating is roughly 100 million times the world energy consumption per year. So obviously it's not possible to make any significant amount of quark-gluon plasma, so that we could in this way study it in laboratory. But fortunately there's another way of creating this matter. So please. And as long as we are satisfied that we are not creating lots of this matter, actually we are creating extremely small amount of quark-gluon plasma. So this we can do by colliding heavy nuclei. This is, for example, lead nuclei or gold nuclei with particle accelerators, and this way we can actually create small droplets of quark-gluon plasma. Currently there are 2 accelerators in the world that can do this. These are LHC at CERN and RIG at Brookhaven National Laboratory. So now the problem is that this created plasma is small, so it's not possible to poke this created plasma directly to measure its temperature or its pressure, but we actually must infer the properties of this plasma in another way. So we have to actually be able to interpret these actual particle accelerator measurements by understanding theoretically very well what happens for this plasma when it's created in these collisions. And this is something, for example, what I have been doing. So the current picture of the plasma evolution is shown now in these 3 figures. So the left figure shows the plasma right after it's produced in these collisions. So the red stuff is the actual quark-gluon plasma. And now the conditions here are pretty extreme. So the temperatures are larger than 10 to 12 kelvins, and pressure is even more impressive. It's larger than 10 to 29 bars. So one can imagine what happens when we have this kind of pressure in this very small system that is surrounded by essentially nothing, so it's surrounded by vacuum. What happens that this plasma starts to expand very violently. It explodes and it breaks into individual particles that form this plasma. And these particles are then that result from the breaking of the plasma are something that we can then eventually measure with the apparatus that we have at the accelerators. Now what we can actually exploit here, please change that. Exploit here is that this plasma droplet is created in very many shapes and very many sizes. So it depends if these colliding nuclei are colliding head-on or they just scrape each other, and it also depends that what kind of configuration these constituents of these nuclei are when they collide. So we can actually create variety of these shapes and sizes, and each of these droplets have different pressure distribution. And now how this plasma actually breaks into a part, then this depends not only on this pressure distribution initially, but then it also depends on the quark-gluon plasma properties. In fluid dynamical limit that we actually are using fluid dynamics to model these plasmas, these properties are pressure and the viscosity of the quark-gluon plasma. So we can actually, by matching experimental results and our theoretical calculation, we can actually probe the properties of this quark-gluon plasma. So this last slide here shows the left-hand side shows then one lead-lead collisions that is measured at CERN. So this is only one collisions, and then these lines here, these tracks actually show the particles that are coming from the collision. So these particles are created when this plasma is breaking up. And now in the theoretical work we have to actually match these measured particles, that how we can create such a distribution of particles by doing these theoretical fluid dynamical calculations that tells how this quark-gluon plasma is actually breaking apart. So in this way we can actually figure out and find the properties by matching experimental work and theoretical work, and we can actually, for example, determine the viscosity of quark-gluon plasma, so we can truly probe the hottest possible matter that we can create in laboratory conditions. So, thank you. So you can ask questions through the chat.
Okay. You said that at the moment only CERN and Brookhaven can produce this quark-gluon plasma. Are there any facilities planned for the future that will be able to?
Yeah, so currently there are these two experiments, LHC at CERN and RIC at Brookhaven, that can produce this plasma. There are actually future colliders that are under construction at the moment, so we can actually see the slightly different conditions for this plasma production. They are not actually higher energy, but they are actually lower energy. That this creates these plasmas that are actually closer to compressing the plasma than heating the plasma. In this way, this actually this can be used to study this plasma under slightly different conditions.
Okay, what is the confidence you have in the simulations? So how well do the simulations relate to the actual experimental results, and how do we know what to extract from them?
Yeah, so the question was that how much I think that these simulations are reliable in describing this plasma evolution. I would say that it depends on the collision. So if we have very central collisions that we create very large amount of this plasma, then I'm pretty confident that at least the most significant features of the plasma are catched by our simulations. But then we don't actually know exactly that what are the limits of our modeling, and this is actually one of the current topics in research, that how we can actually expand the limits of our model to even smaller plasmas. So if we have this list of these different shapes and sizes, so how we can extend this our models to even the smallest droplets of plasma that are created. So this is.
Is there a reason why you are using those heavy particles colliding to each other?
Yeah, of course, is the reason to why we are using heavy nuclei in this collision. So reason is obvious that we want to create as much as possible this plasma, and using heavy ions makes it possible. So in that sense we use as heavy ions or nuclei as possible. But on the other hand, we are also currently, there is a research program that active research for the smaller collision systems like xenon or even maybe in the future even oxygen nuclei. And then we are really probing the limits of our understanding, that when does this plasma really form, and when we can describe it by using the tools that we have currently available. So, but the easiest condition is that if we create as much as possible the plasma, so that's why the heavy ions are used.
Can you give like some kind of answer about the time scale of these collisions, that what they are?
So question first, what is the time scale of these collisions? So actually the times are shown in the slides, and let's say that in these collisions we actually measuring these times as a function of femtometers. So actually femtometer is time that what it takes light to go distance 10 to the minus 15 meters, so these are extremely small time. So this is basically time what it takes light to cross the nuclei. So in seconds this is something like 10 to minus 23 or whatever or that second, so it's really extremely small lifetime. So we can figure out these plasma properties only through comparison between the theoretical work and the experiments. Okay, thank you.
We have a question, which is what kind of software you use in fluid dynamical simulations in recreating the conditions?
Yeah, this software is actually written by myself. So one reason is that actually when we use fluid dynamics in this kind of environment, we have to take into account Einstein's theory of relativity, and we also need to take into account that this system is extremely small. So this also brings modifications to the usual fluid dynamical models. So currently I'm using the own codes that I have written from scratch myself.
Usually a simulation of a collision, how long does it take in computing terms, and also how heavy is it in terms of computing power?
So the question is that how long actually these fluid dynamical simulations take. So that depends a little bit at what kind of approximation and what kind of resolution we use, but usually let's say that one simulation of one of these events takes roughly one hour. And this is not a problem, but the problem is that we actually have to make tens of thousands of these runs to analyze one particular type of experiments, because reason is because we create in so many different initial conditions and shapes on this plasma that we have to basically account significant part of different shape before we can compare to the experiments. Okay, so that was the end. So thank you for everybody for listening.